welcome. In my previous lecture, we have discussed a ratio estimator for estimating the finite population mean, finite population total, and population ratio. We have discussed the bias and variance. Now, we have seen that the variance of the ratio estimator is given by 1 minus f by n into sy square plus r square sx square minus 2r syx, where we have sy square equal to 1 by n minus 1 summation I equal to 1 to n yi minus y bar whole square, sx square equal to 1 by n minus 1 summation I equal to 1 to n xi minus x bar whole square, and syx, that is equal to 1 by n minus 1 summation I equal to 1 to n yi minus y bar into xi minus x bar. Now, using these values, we can get another expression for variance of yr bar, which is easy to compute. Now, using this, we can get variance of yr bar, that is equal to 1 minus f by n into 1 by n minus 1. This will be summation I equal to 1 to n. This will be yi minus y bar whole square plus r square summation I equal to 1 to n xi minus x bar whole square minus 2r summation I equal to 1 to n yi minus y bar into xi minus, this is variance of yr bar equal to 1 minus f by n 1 by n minus 1 summation I equal to 1 to n. This will be yi minus y bar whole square plus r square xi minus x bar whole square minus 2r yi minus y bar into xi minus x bar. This is equal to 1 minus f by n into 1 by n minus 1 summation I equal to 1 to n. This will be yi minus y bar minus r xi minus x bar whole square. Now, this is equal to 1 minus f by n 1 by n minus 1 summation I equal to 1 to n. This will be yi minus y bar minus r xi plus r x bar whole square. So, where we have r equal to y bar by x bar. So, r x bar, this will be equal to y bar. So, y bar will cancels out. So, that means this will be 1 minus f by n 1 by n minus 1 summation I equal to 1 to n. This will be yi minus y bar minus r xi plus this will be y bar by x bar into x bar whole square. So x bar will cancel out. Again this y bar will cancel out. So this will be equal to 1 minus f by n, 1 by n minus 1 summation I equal to 1 to n yi minus r xi whole square. So this is easy to calculate. So that means this will be 1 minus f by n into 1 by n minus 1 summation I equal to 1 to n. This will be yi square plus r square xi square minus 2r yi xi. So this is now equal to 1 minus f by n, 1 by n minus 1. This will be summation I equal to 1 to n yi square plus r square summation I equal to 1 to n xi square minus 2r summation I equal to 1 to n yi xi. So that means we have to compute summation yi square, summation xi square, summation yi xi, I equal to 1 to n. So that this formula can be used for calculation of variance of y bar very easily. Now similarly we can also find an unbiased estimate of this. So as we have seen that variance of y bar equal to 1 minus f by n into sy square plus r square sx square minus 2r sy x. Now an unbiased estimate of sy square is given by the sample mean square sy square, that is equal to 1 by small n minus 1 summation I equal to 1 to n yi minus sample mean y bar whole square. Similarly an unbiased estimate of s square is small sx square, and unbiased estimate of syx is small syx, that is equal to 1 by n minus 1 summation I equal to 1 to n yi minus y bar into xi minus x bar. Now using this estimate of variance of y bar is given by 1 minus f by n sy square plus r cap square sx square minus 2r cap s yx, where r cap equal to small y bar by small x bar. Now on simplification also we can write estimate of variance of y bar, that is equal to variance of y bar estimate, that is equal to 1 minus f by n into 1 by n minus 1 summation I equal to 1 to n yi minus r cap xi whole square. By simplifying in the similar manner we can find also summation yi square, summation xi square and summation yi xi, and we can find the estimated variance of sample ratio estimator of the population mean. Now we can see that the ratio estimator of the population mean is a biased estimator, and its bias becomes negligible when r, the population ratio, is close to beta. Beta means the regression coefficient of y on x. Now This is up to first order of approximation, but several attempts were made to find the unbiased ratio type estimators. Now, how to get unbiased some ratio type estimators? There are different methods, and the simplest method was suggested by initially the Hartley and Ross in 1954. So, unbiased ratio type estimator. So, under this, first we shall study the Hartley and Ross unbiased ratio type estimator. Here, this is a simple technique which is used in the construction of unbiased ratio estimator to adjust an estimator for its bias. An unbiased ratio type estimator was proposed initially by Hartley and Ross in 1954 in case of simple random sampling without replacement scheme. Suppose a simple random sample of n units, is selected using without replacement scheme, and we calculate xi and yi for all the units of the sample. Then we calculate the ratio, mean of the ratios. We define Ri equal to yi by xi, I equal to 1 to n, and Rn bar equal to 1 by n summation I equal to 1 to n Ri, that is equal to 1 by n summation I equal to 1 to n yi by xi, and this is the mean of the ratios. And R cap we have obtained, that is equal to R. This is yi bar, y bar, this is y bar by x bar. This is the ratio of means, that is the difference. So, we use this Rn bar to reduce the bias of the ratio estimator. Now, similarly for the population, let us define Rn bar, capital Rn bar, that is equal to 1 by n summation I equal to 1 to n yi by xi. This is for the population, 1 by n I equal to 1 to n Ri, where Ri equal to yi by xi. So now consider an estimator y r bar dash, that is equal to Rn bar into x bar. This is estimator based upon the mean of the ratios Rn bar x bar. So this is expectation of y r bar dash, that is equal to expectation of Rn bar into x bar, that is equal to Rn bar into x bar. This is not equal to y bar. So this y r bar dash, this y r bar dash, this is also a biased estimator of the population mean. So now what will be the bias? Now we have bias of y r bar dash, that is equal to expectation of r n bar x bar minus y bar, that is equal to r n bar x bar minus y bar. So this is equal to, we can take minus common, this is y bar minus r n bar x bar, that is equal to minus, this is 1 by n summation I equal to 1 to n, this is yi, this is the formula for y bar, minus r n bar x bar. So that is equal to minus 1 by n, taking common, this will be summation I equal to 1 to n yi minus n r n bar x bar. So this is equal to minus 1 by n summation I equal to 1 to n. This can be yi by xi into xi minus n r n bar x bar. Now this is minus 1 by n summation I equal to 1 to n, this is ri xi minus n r n bar x bar. So this is equal to minus 1 by n summation I equal to 1 to n, this will be ri minus rn bar into xi minus x bar. This is just like the covariance formula. So that is equal to minus n minus 1 by n s r x, where s r x equal to 1 by n minus 1 summation I equal to 1 to n minus 1 ri minus rn bar into xi minus x bar. This is the SRX, this is the population covariance between R and X. Now if you define small SRX, that is equal to 1 by n minus 1 summation I equal to 1 to n ri minus rn bar into xi minus x bar, that is equal to n by n minus 1 y bar minus rn bar x bar. So that this is expectation of SRX equal to SRX. So we can find an unbiased estimator of this SRX as SRX. So now we have seen that the bias of y bar, this is equal to minus n minus 1 by n expectation of small SRX, where small SRX is defined by this equal to 1 by n minus 1, I equal to 1 to n, Ri minus Rn bar into xi minus x bar. So this is equal to 1 by n minus 1 summation I equal to 1 to n. This is Ri into xi minus x bar. This is equal to summation I equal to 1 to n Ri xi minus x bar summation I equal to 1 to n, this is Ri, whole divided by this is n minus 1. Now this is equal to summation I equal to 1 to n Ri, Ri is equal to yi by xi. So Ri xi, this will be yi, summation I equal to 1 to n, this will be yi minus x bar summation I equal to 1 to n xi divided by n minus 1, because this is Ri equal to yi by xi. So now this is equal to summation I equal to 1 to n yi minus x bar, this is Ri, x bar, no, see, now this is equal to n into y bar minus x bar, this will be n into Rn bar divided by n minus 1. So this will be equal to n by n minus 1 into y bar minus Rn bar x bar. Now here the expectation of SYX where SRX equal to this. Now we can use this value to find an unbiased estimator of the bias. An unbiased estimator or bias of YR bar dash is given by, this will be equal to minus n minus 1 by n into n by n minus 1 y bar minus Rn bar x bar. Now Hartley-Ross estimator of the population mean is given by y bar, this is Hartley-Ross, that is equal to YR bar dash minus unbiased estimator of bias of YR bar dash. So this is equal to YR bar dash minus, this is unbiased estimator of bias is this, so this will be plus n minus 1 by n by n minus 1 y bar minus Rn bar x bar. So this is the Hartley-Ross estimator of the population mean. So the Hartley-Ross estimator of the population mean is or can be written as y HR bar, this is equal to y R bar dash plus n into n minus 1 divided by n into n minus 1 into y bar minus Rn by x bar. So this is the Hartley-Ross estimator of the population mean. Now when n is large, sample size is large, then n into n minus 1 by n into n minus 1, this will be approximately close to 1. So, and also Rn bar is close to Rn bar. So, the Hartley-Ross estimator now reduces to Rn bar x bar plus y bar minus Rn bar x bar. Now this is equal to y bar minus Rn bar x bar minus x bar. So that expectation of y HR bar Hartley-Ross, that will be equal to y bar. This will be 0. So the Hartley-Ross estimator is a ratio type estimator and which is almost unbiased for estimating the population mean y bar. Now we have to find the variance of this Hartley-Ross estimator y HR bar. So for the variance we consider y HR bar, that is equal to expectation of y HR bar minus y bar whole square, that is equal to expectation of y bar minus y bar minus Rn bar x bar minus x bar whole square. Now this is equal to expectation of y bar minus y bar whole square plus Rn bar square x bar minus x bar whole square minus 2 Rn bar y bar minus y bar into x bar minus x bar. So this is equal to, this is variance of y bar, so this is approximately equal to 1 by n sy square plus Rn bar square, this is sx square minus 2 Rn bar is yx. Now this is the variance of Hartley-Ross estimator. Now we have to compare this Hartley-Ross estimator which is unbiased with the ratio estimator, simple ratio estimator. So now the comparison between Hartley-Ross estimator and the usual ratio estimator y R bar. We have seen that variance of the usual ratio estimator y R bar equal to, this is for large n, this is 1 by n sys square plus r square sx square minus 2r syx, and variance of Hartley-Ross estimator, this is equal to, approximately equal to 1 by n sy square plus Rn bar square Sx square minus 2 Rn bar Syx. Now variance of yr bar minus variance of y hr bar, this is equal to 1 by n. So here sy square this will cancel out, so only we will have r square minus Rn bar square into Sx square minus 2 r minus Rn bar Syx. Now we have the population correlation coefficient rho between xy is Syx by Sy into Sx. So Syx equal to rho into Sx. So this will be equal to one by n. So Sx square we can take common, Sx square by n into r square minus Rn bar square minus 2 r minus Rn bar into Syx by Sx square. So Syx by Sx square, this is beta, the regression coefficient of y and x. So now this will be equal to Sx square by n r square minus Rn bar square minus 2 beta r minus Rn bar. This variance of yr bar minus variance of y hr bar, this is equal to Sx square by n into r square minus Rn bar square minus 2 beta r plus 2 beta Rn bar. Now this is equal to Sx square by n r square minus, this is 2 beta r plus beta square minus Rn bar square minus 2 beta Rn bar plus beta square. So now we add here beta square minus beta square. So this is equal to Sx square by n. This will be r minus beta whole square minus Rn bar square minus beta whole square. Now from this, the preference of the ratio estimator or Hartley-Ross estimator depends upon this term. That means whether r is close to beta or Rn bar is close to beta. So if r is close to beta, then this term will be 0. So we have this becomes negative. So we prefer a ratio estimator, usual ratio estimator. Now suppose Rn is close to beta, then this term will be 0, then this will be positive. Positive means we have to prefer Hartley-Ross estimator. So the preference between the Hartley-Ross estimator and usual ratio estimator depends upon the closeness between R, beta and Rn bar. If R is close to beta, we prefer ratio estimator. If Rn is close to beta, we prefer Hartley-Ross estimator. This result is due to Godman and Hartley in 1958. So in our next class we shall discuss other almost unbiased ratio estimators, preferably Q-knowledge almost unbiased ratio estimator. Thank you.